Okay, good evening, all of you. So, I think I'm audible and the page is visible to you, right?
Ma'am, yes, ma'am.
Yes,
Okay,
ma'am.
fine. So, today we'll start our unit 10. So, basically, from the beginning itself, you are very clear that with this spectroscopic method, you are having 14 units, 1 4. So today we'll be starting the unit 10, which is atomic emission spectroscopy. So with this unit 10 as well as unit 11 is there, which is the application of AAS, atomic absorption spectroscopy, and atomic emission spectroscopy. With 11th unit, we'll finish our atomic spectroscopic parts. Then unit 12 is about your NMR spectroscopy. Then unit 13 is your mass spectroscopy. Then final unit, which is 14, that is just the structural elucidations, the numericals, like that it is there. Unit is mostly application of this kind of spectroscopies. So coming to atomic emission spectroscopy, this unit also you will have a feelings the same as your atomic absorption spectrometry, flame photometry, and that kind of feeling you will have. But atomic emission spectroscopy, here we'll be using some different technique here. In the last class, we discussed about your atomization by using your graphite furnace, by using the flame photometry, but flame way atomization is having certain limitations. We saw that. So, electrothermal way of atomization means by using graphite furnace, it becomes quite easy. Easy means it becomes quite sensitive, and it is quite good as a in order to find out the atoms in a good way. But here we'll see the atomic emission spectroscopy. So atomic absorption you came to know, but emission spectroscopy, how we will be getting a good emission spectrum out of the process, that we have to find out. So in the current unit, we will be taking up the atomic emission spectroscopy that basically concerns with the emission of radiation by suitably excited atomic vapors of the analyte. Okay, so initially your excitation of the atomic vapors will take place, then followed by your emission. But here we'll be using the concept of plasma chemistry. So this may be little new to you, but it's a good thing to know through this program. Plasma chemistry, little bit concepts, because here not much in depth is there, but whatever is there in your course, it is good enough to know about the plasma chemistry, know about the plasma. So here the emitted radiation and its intensity forms the basis of the qualitative and quantitative application. Means your emitted radiation and its intensity, because intensity of the emitted radiation is proportional to your concentration. Okay, so in that way, you can do the quantitative analysis as well as qualitative analysis. You can do by seeing the emitted radiation and their intensities. Okay, so AES is one of the oldest spectroscopic methods of analysis. It is a multi-element analytical technique. Okay, it's a multi-element analytical technique, but there is limitation also. Whenever you are doing multi-element analysis technique, then that time what you have to do? You have to do deal with various radiation sources. You have to change the sources. So many parameters also you have to change, like the way we discussed in the last class, AAS, atomic absorption spectroscopy. There what we saw, that for element to element you have to change the source of your radiation source, then you have to change your monochromators accordingly. Suitability wise, you have to change. So that is the difficulty with this kind of technique. However, this particular atomic spectroscopies gives a good result and accurate results as far as your pH metric, conductivity metric, other techniques you will be following, other gravimetric analysis techniques. But these are very sophisticated and accurate results you will be getting. Okay, so it's a high detection power. Detection power is very good. That is why the spectroscopic methods are having the good detection limit. Okay, so it's a high detection power and wide variety of excitation sources make it the most extensively used method of analysis. Yes, we understand that wide variety of your excitation sources is needed, but that also makes the most extensively used method of analysis, because you want to study some element, then other element, then other second element, like that. Then by tuning the source itself, you can just do the analysis. It need not to be all the time you have to change the source. No, for a particular thing, certain elements you can characterize, then you can go for that. Then for some other range of other window or other range of studying the elements, you can you go for the another radiation source. So, of the various different atomic emission spectroscopic methods, so various atomic emission spectroscopic methods are there. We will deal with one in which the inductively coupled plasma (ICP) acts as an atomization and excitation source. It acts as the atomization as well as excitation source, the technique being called ICP-AES, inductively coupled plasma atomic emission spectroscopy. So here you are using the plasma source for the atomization as well as for the excitation source. Okay, ICP AES we called it as. So the principle of the atomic emission spectroscopy, what is that? As we are always discussing about principle of any spectroscopy while moving towards the elaborate discussion about that spectroscopic part, always we are discussing principle, and the principle more or less by this time you might have understood that all the spectroscopic methods are based on one principle, that is radiation and matter interaction. If it is coming to molecular spectroscopy, then directly hitting up this radiation with the matter is happening, that you are just passing through the filter or monochromator, making it monochromatic, then it is falling, it's fine, that is the way. But overall what we are doing, we are just interacting the radiation and with the matter, then we are going to collect the uh, reading outputs. But here in just making the solution phase of elements to the atomic species we are creating, means atomization is getting done in the vapor phase, then we are studying it further. So in atomic emission spectroscopy, AES, a reproducible and representative amount of the sample is introduced into an atomization excitation source, where it is converted into atomic vapors of the analyte in the excited state. So that is the main motto for all the atomic spectroscopies till now we have studied. Okay, atomization and excitation you have to do. Then it is going to the excited state. Then it is if you are just studying atomic absorption, then you can stop over there. But if you are studying atomic emission spectrometry, then you have to concentrate on the emission radiation that is coming out of that. Okay. So in flame photometry, you have observed that the analyte solution, when it is introduced into the flame, undergoes a number of purposes to be atomized. Okay, there are number of processes of atomized. Then it get excited. So as the excited state is short-lived, so excited atoms return back to the ground state after a very short lifespan, means within a time scale of your 10 to the power minus 6 to minus 9 second. Mostly it is nanosecond time scale. So this is accompanied by emission of electromagnetic radiation, normally in the form of light in the UV visible region. We are dealing with the emission absorption. All concepts means it is we are dealing within the UV visible region only. Okay, there only you will wear Lambert's law or your Franklin principle, Bonhoeffer approximation. These principles gets applicable over here. So this radiation is the characteristic of constituents of the sample. The emitted radiation which you are seeing, that is the characteristic constituent of the sample. Here I want to just trying to tell you one concept that just imagine in your mind you are having a sample solution, and the molecules which you want to study or atoms you want to study, its surrounding will be different. Okay, its surrounding will be different. Suppose your box A is there and box B is there. In box A, the environment may be different. In box B, the environment may be different. While you are taking the excitation or emission spectra, the result, whatever you want to study, that is the absorption spectra you are getting or emission spectra you are getting, you will be getting in different way for box A sample and box B sample. Then we have to do one thing, you have to characterize that spectrums. You have to analyze that spectrum either by your theories or by reading so many literatures from the research point of view. You have to study that things. Then only that radiation, why this sentence is there? This radiation is characteristics of the constituents of the sample. The radiation or the spectrum, whatever you got, that is the characteristic of the constituents of the sample. So what kind of sample is in box A, what kind of sample is in box B, whatever radiation you are getting, whatever spectrum you are getting, that will indirectly tell you about the constituents of the sample or environment around the sample. Okay, so due to the resolution of the emitted radiation generates an emission spectrum whose detailed analysis can be exploited to obtain the quantitative as well as qualitative details of the analyte. Understood? Whatever emission spectrum you are getting, the detailed analysis, if you do, you can get very, very important aspects of the qualitative as well as quantitative details. Here, the purpose of the class is just to show you the path and to make you understand about this kind of spectroscopic methods. But when you do practically, experimentally, that time you will be facing many problems. That time you will be facing many trial and error you have to do. You have to follow many research articles about that. So many things are there also. But as all of you know, that fundamental or the main brick should be strong enough. So main concepts should be clear. So the versatility of this AES is due to availability of a wide range of atomization excitation sources. So various sources are available. That is why these are very effective method to study. Okay. So the atomic emission spectrometry based on plasma sources. Okay, this you see the sun, lightning, and aurora. Aurora means that lightning effect you are seeing. Okay, borals are examples of plasmas found in nature. Plasma is a high source which, which is an electrically neutral conducting gaseous mixture having significant concentration of your cations and electrons. So plasma is a high source, high energy source radiation. Okay, high energy source you can say, and it is electrically neutral, but it is electrical conductor. It is an electrical conductor. Electrically neutral means it is having the positive and negative parts, whatever is there, it is almost equally maintained. That is why electrically neutral. But due to that charge species whatever is present in the plasma, that makes it as the electrical conductor. Understood point? So that makes the plasma to be electrically conducting thing. So it is a high source, high energy source, which is an electrically neutral conducting gaseous mixture having a significant concentration of cations and electrons. Okay, so as an electrical conductor, it can be heated inductively by coupling with an oscillating magnetic field. So these things you can you can provide it oscillating magnetic fields to have a inductive effect over here, and the temperature of the plasma may be of the order of this. Here, just I want to remind you that in the last class, the graphite furnace we saw, that graphite furnace or electrothermal way of atomization, we observed that 1500 to 3000 Kelvin, up to that temperature we can handle with the electrothermal furnace, graphite furnace. Okay, so whatever elements you can get the atomization within that range, that only can be studied by using graphite furnace. But what about the elements which you can study at like more than 5000 K? If this much temperature is needed for the atomization, then you have to go for the plasma way of atomization, where you can maintain the temperature of the order of 5000 to 8000 Kelvin. Okay. So the plasma based is in principle is similar to flame photometry, but the only difference over here is being that the flame is replaced by much more energetic atomization excitation process using plasma. This is the only difference in flame photometry as and your atomic emission spectrometry based on plasma source. Here you are changing the source as plasma. Why? Because you can maintain the temperature, the elements which are showing the atomization above 5000 Kelvin. You can use that here. Okay. So in emission work, the argon plasma is frequently employed. Argon plasma is mostly used, okay, because this is your inert one, and why so also we will be subsequently seeing it. So the analyte sample, what you have to do first, the analyte sample is introduced into the center of the plasma as an aerosol with the help of nebulizer using argon flow. That is the normal procedure which you do. Then, as in the flame, in plasma also, the sample undergoes various transformations like your dissolution, vaporization, atomization, ionization, then excitation. Okay, those have attended my flame photometric class, they can understand it very easily. Those have missed it, then they can understand here also, because the same principle is getting applied here. So the excitation and ionization occurs due to collisions of the analytical atoms with high energy electrons. The high temperature assures that most of the samples are completely atomized. So this is the difference of using plasma based AES instruments, because you are maintaining high temperature, you are assuring that complete atomization of the species is happening. However, some molecules like this, because some molecular based molecular species will be there, breaking them and atomization of them is difficult. That also do exist in plasma and are also measurable. As the energy of the plasma source is quite high, it ensures the excitation of the atoms of all the elements present in the sample, which then relax by emitting electromagnetic radiation of characteristics wavelength of different elements. That is why, since it is making sure of complete atomization, so you can go for the multi-element analysis study. You can go for the studying multi-elements over here. Okay. So these are the things where your cerium you want to study. But since this is a multi-elemental technique, so some species while studying a particular thing, due to the nearby species whatever is present, that atomization also will happen. Okay, so that is the interference over here. A representative atomic emission spectrum based on plasma is given in your figure 10.1, which I was showing. It shows an ICP-AES spectrum of cerium having a concentration of 100 picomole. So you may note here that presence of a number of lines from the analyte. Just see here many number of, including cerium, you are getting many number of continuum lines. So as the source gas is argon and the molecular species and other background radiation also will interfere over there. So this could give you an idea of how to expect for a multi-element analyte, how to go for the multi-element analyte. Well, whichever you want to focus, you have to focus there only. The rest elements, whatever is coming into picture, you can avoid that, as well as you can just go for the further article study, literature study. Then you can also see how to eliminate the things. So, an ideal atomization excitation source should have the following your characteristics. Okay, it should completely separate the analyte from its original matrix as to minimize the interference. One ideal atomization excitation source we are talking about. Remember this thing. Nothing is ideal. Nothing is ideal. But if it is a ideal atomization excitation source, then these are the these characteristics it should have. But nothing is ideal. So it should be completely separate the analyte from its original matrix so as to minimize the interference. But minimization interference is sometimes it is very difficult while studying the spectroscopic methods. But there are techniques to it. We have to follow that as far as you can minimize the interference. So it should have appropriate energy to ensure complete atomization. Okay, and but keep the ionization to a minimum. So it should have proper energy, appropriate energy to ensure complete atomization process. So it should provide an inert environment so as to keep the undesirable molecular species formation to a minimum. So much other molecular species interference is not good. So more the inertness of the environment, more good result we will get. Okay, and the interference due to other molecular species will be minimum. It is not mentioning that completely it will get eliminated. No, the molecular species formation can be minimum. So it should have none or eligible background radiation. So background radiation should be very less so that it will not create any spectral interference. Last class we were discussing what was that spectral interference. So due to spectral interference, you can avoid that. Okay, it should have if it is having non or negligible background radiation. Then it should provide for the analysis of samples in all possible forms like solids, liquids, gases, slurries. Then all the things, if you are putting energy, they all will be converted into vapor state, then atomization will happen. Of course, it should be inexpensive. That is the most desirable condition. It should be inexpensive, need minimal maintenance, and easy to operate. Because these three things, from spectroscopy technique to technique, it varies a lot. Like if you are going to go study a fluorimeter, the instrument I was showing you in my fluorescence class, which we bought here, that costs 30 lakh. If you go for UV visible, that will cost around, many good are there also, but that will cost around 10 to 15 lakh. But if you are going for the NMR spectrophotometer, it costs 2 crore. So sometimes the methods which we want to study, we are studying the concepts, it's fine. But if you really imagining now in your mind that, okay, I'll just do water analysis and I'll go for soil testing, these elements, I will study this, that. But you have to see what is your laboratory condition, what instruments you are having with you, or what nearby instruments you are having, you can go for it or not. If you are using some inexpensive and minimal maintenance instruments, then it's and easy to operate, then you should go for these things. Okay. So, choice of argon as the plasma gas. Many gas you can use helium, argon, and nitrogen mostly getting used as the plasma gas. However, this argon is the best one out of all. So there are some regions for which the argon is chosen as a plasma gas. So, argon being an inert gas, while working in the laboratory, you will be seeing some nitrogen cylinder or oxygen cylinder. You have, like in hospitals, also you are having oxygen cylinder. Similarly, the nitrogen cylinder, gas cylinder, everything is available in the market also. For the purpose of research, whenever we need, we bring that. Okay, argon cylinder or nitrogen cylinder, whatever you want to purse. So, argon being an inert gas doesn't form stable compounds with the analyte elements. So that is what is needed. We don't need any interference with the analyte elements. It should not form any compound with the analyte elements. So therefore, there would be lesser chemical interference in the event of the atomization of plasma. That is the best thing with the argon. Then, as its emission spectrum is relatively simple and it is optically transparent in the UV visible region of the spectrum, it doesn't offer spectral interference in the emission spectrophotometer. What is happening? Its emission spectrum is relatively simple and optically transparent. This argon gas is optically transparent in the UV visible region of the spectrum. So it will not offer your spectral interference. Last class we were discussing about the spectral interference. Mostly if you are using argon, this thing can be avoided, spectral interference. Then argon has a moderately low thermal conductivity, so the heat is retained within the plasma firewall and sustaining stable operation at a moderate power, inputs. So since it is having low thermal conductivity, what will happen? The plasma temperature, whatever you want to maintain the plasma temperature for a specific analyte to be studied, that can you can maintain it because it is as such this gas purging the argon you are passing the argon that will have low thermal conductivity. So, as the abundance of the argon is reasonable, that is 1% in air, it is economical also. It is economical as compared to other noble gases. So, as the last point is the fast ionization energy of argon is quite high. It has the capacity to atomize, ionize, and excite most of the elements of the periodic table, which in turn permits the determination of almost all elements that can be excited to emit the lines in the UV visible region. So this is the best parts you saw with the argon. Okay. So nitrogen has also been used as the plasma gas, either alone or mixed with the argon. However, as excited nitrogen emits a complex band spectrum that can cause undesirable spectral interference, maybe due to nitrogen. You may get spectral interference which is not there in argon, so better to go for argon. So that is why it has not been widely adopted. Nitrogen is not been widely adopted. Okay. Some investigators have also carried out the experiments by using helium plasmas. However, due to your high thermal conductivity, it is having high thermal conductivity. If it is having high thermal conductivity, then maintaining the temperature will be difficult for you. Whilst doing the experiment, maintaining the temperature will be difficult. So the high conductivity of this helium of the gas, consequent higher power inputs make this also not a favorable choice. So helium also not a favorable choice. Okay. So here you can see the things that plasma properties, that electrical resistivity, thermal conductivity, and then specific heat of three gaseous molecules, that is argon, nitrogen, and helium. But out of that, that was the best argon. Coming to instrumentation, here I am just first showing you the figure. So keep in mind this figure. So you are having the sample, this is the nebulizer, then this is the plasma unit. Like the way we have our flame photometry flame unit. Then monochromator will be there, then detector, then signal processing and computer system. That is a reading output thing. So here the plasma source as an source, radiative source, then nebulizer, then your monochromator, detector, and this thing. Okay, sample is getting spread. Then no, first there should be nebulizer. First there should be nebulizer. Then your plasma unit is coming, and through this your atomization in plasma is happening. Okay, then it is just monochromator. Through monochromator you are just collecting the radiation coming out, then detector will detect that and amplify it, then signal processing will be done, and reading output device you can see the thing. So sample introduction, how it happens that the inductively coupled plasma emission spectroscopy is used primarily for qualitative and quantitative analysis of samples that are dissolved or suspended in aqueous or organic liquids. Okay, the sample is brought as a fine aerosol into the plasma. It is brought as a fine aerosol into the plasma, which is generally achieved by pneumatic nebulization. Okay, these are carried out into the torch by argon gas flowing at a rate of some with a particular rate through the central quartz tube. Here, the central quartz tube is there. Okay, argon gas will be getting passed through this. So, this aerosol, which you are going to spray that sample, it will pass through this quartz tube that is centrally available here. That will be passed through this one by a flow of your argon gas, flow of your argon gas. Then this atomization over there, that argon gas, it will be passed at a certain rate, so that it will also inductively coupled through the magnetic field, and there will be ionization of the elements as well as plasma will get created, which is of high temperature, and there will be atomization of the species you want to study. Okay, so this is the thing you can see. Like the way, if you remember graphite furnace we had used, there you didn't have any flame. You didn't have any flame. Here you see argon purging is getting done through this argon plus purging up to here. Then here graphite rod is there where your sample you are keeping like this. But these techniques are very, very sensitive techniques. Sample you are just putting here in this graphite rod cavity. You see the cavity, this red mark you are able to see. In this red mark, small cavity is there. Small cavity is there. Sample you are just putting like this. You don't imagine that, okay, graphite rod, it has been placed like this. I will just use my hand and take the sample and keep over there. No, you have to pass it with a uncontaminated syringe or microtips. You have to use that kind of things over here. Okay, you have to keep them. And then the automatically your system is such a way that argon flow will be there, then atomization, and this plasma will get created. Okay, then you are having monochromator. Emission from the plasma is usually polychromatic in nature, okay, which implies that it consists of a large number of radiation of the different wavelengths. So you have to cut the unrequired, the undesired different wavelengths of radiation. You need to get a monochromatic radiation which you want to go for the studying the thing. Okay, so in ICP AES spectrophotometer, the resolution of the complex spectra is achieved using ruled grating monochromators having large number of groups on the grating. During my fluorescence class, I was telling you that grating monochromators are having many groups. Okay, and the resolution of the complex spectra can be managed, or resolution you can get in a better way if you are using a grating monochromator, because The collective radiations you are going to get, monochromators are there, getting monochromator, prism monochromators, but by using grating monochromators, these radiations which you are going to fall on it, they will convert it into a specific way, and they will make it a monochromatic with a good resolution. So you'll be getting a better resolution out of that. Then detector can be these are of photomultiplier tubes, photodiode arrays, charge coupled devices, like this kind of any detector also can be used. Okay, mostly photomultiplier tubes are getting used. Then your reading output device is there. So through the output device, you can get your spectrum. You can get the spectrum whatever way you want, or then further also you can analyze it very clearly, which element is present, which not. So don't you don't have to worry. Like by seeing all these things, you will be thinking, Madam, how to know this element is present, that element is present. There are also, we are talking about the methods. There are also in instrument this read output device which we are discussing. There are also softwares are there. Softwares are there to tune the things, to know the particular wavelength, to know the particular maximum peak. Everything is there available. So you don't have to worry for that. So qualitative analysis using ICP-AES, how to do that qualitative analysis? Actually, it's difficult. In principle, it is possible to obtain the qualitative information from ICP emission spectrometry by using sequential spectrometers. However, this technique has not been exploited for the purpose of your qualitative analysis. It has not been exploited. Means large scale, this qualitative analysis studying is a point of research and it is going on. So this is so because the amount of sample and the instrument time required are prohibitive. So much time is needed over here also to set for a single element. Similarly, as it is almost impossible to install individual photomultipliers to monitor multiple lines for each possible element of interest, the direct reading spectrometers or polychromators are also not used for qualitative analysis method. Okay, to some extent, it is used for the qualitative purposes. To some extent, due to these limitations of changing the things and so. So coming to the quantitative analysis part, here you can see, here the graph you see, this is analyte concentration and here is your intensity, whatever you are going to get from the peak, get from the your AES peak, whatever you are getting. Okay. So here in the x-axis, you are just changing the concentration of the sample, and in the y-axis you are just following the intensity. Okay, so the strength of this ACP AES lies in the quantitative analysis, not in the qualitative part. Qualitative analysis techniques are very sensitive things. Quantity wise, you can find okay, this much amount and concentration, even from the UV visible also you can find. Qualitative analysis are little difficult, but spectroscopic methods are good enough to study qualitative analysis as far as fluorescence emission is concerned, as far as your NMR, mass, IR is concerned, that also are good for the qualitative analysis. Means structural elucidation parts. UV visible also. So the intensity of an elemental atomic or ion lines is used as the analytical signal in quantitative atomic emission spectrometry. So in fact, the spectral intensities are, some noise is coming there. Nages, can you please mute yourself? Okay. Can you mute yourself? Except myself, others can mute yourself. So it will be better. Okay, fine. Where I was. So, in fact, the spectral intensities are unequivocally related to the elemental concentration in the analyte. However, in practice, the AES is a relative method. It is a relative method, okay, and a calibration has to be performed. Wherever we are saying a relative method means relative to your reference sample, relative to your some standard sample, it has to be there should be a calibration plot to it. Once the analyte matrix is understood and the background and spectral overlap correction details have been worked out, the calibration of instrument becomes rapid and straightforward. Okay. Once the background and spectral overlap correction is done, that can be taken care. Here I want to tell you one thing. It got to my mind now that while studying the UV visible spectrometry, we were using reference, if you remember, reference. So always you can do one thing whenever you are taking a spectrum. If you are getting a spectrum and some noise, background noise is coming, how to avoid that? You can do one thing. Take a blank spectrum. Take a blank spectrum means without sample. That blank spectrum you are going to get some signal. Okay, after taking the sample, after studying the sample, whatever spectrum you are getting, just subtract the blank spectrum. The data you will be getting in the reading output device. From there, you can subtract the blank spectrum. Then only you can just avoid this interference due to any other thing apart from the analyte. That can be done. Okay. The analyst, however, doesn't need to bother about making the calibration standards as high purity multi-element plasma calibration solutions are commercially available. Okay. The calibration curves most often consist of a plot of output current or voltage of transducer as a function of analyte concentration, or you can say in form of intensity with that of analyte concentration also can be plotted out. For large concentration range, log-log plots are also employed because of the clarity. Log plots if you are taking, then also you can get for large concentration of the samples. So if less samples are there, it's fine. But if more samples are there, you can go for the log samples. So interference in ICP and AES. So we are having spectral interference, the way we were discussing in the last class. Then chemical interference and physical interference, all these things are also there. So spectral interference, how it comes first by the following, that is overlap of a spectral line from another element, like the way we saw one for the cerium. If some another element you are not putting in, but while taking the sample, you have you might have purified the element, But if some other element is present in some amount, then it is creating the problem. Like the way now we are getting noise from other signals. So, uh, Nagesh Chaudhary, can you just mute yourself? Thank you. Okay. Now we have avoided the spectral interferences. Just let me take some water. Thank you. So, okay. So, whatever analyte you want to study, apart from that, if some other elements are present over there as a contaminant, then that overlap of the spectral line also can cause the interference. So, unresolved overlap of molecular band spectra, that also can be happen. Then recombination phenomenon means some overlapping, means completely overlapping, and recombination may happen sometimes. And background emission from the source itself can also be there, and stray light from the line emission of high concentration elements can also be there present. So in order to avoid these things, as I was telling you, what we normally do, that if some I am getting a fluorescent spectra, if I am getting some background emission from the source, that also I can predict. In fluorescence, I am using Ginel lamp. So take the spectrum of the Ginel lamp. Okay. If in your emission spectra, any Ginel lamp part is coming, you are expecting that, then you can deduct it. Okay. If I'm not expecting in that region, it's fine. Sometimes it may not be there. But if you are going to get due to some other elements, then that parts can also you can subtract. But you have to see which technique you are using. Technique to technique it may vary also. But the spectral interference can be minimized like this. Any interference can be minimized, may not be avoided completely, but it can be minimized. So physical interference, when you say apart from the spectral interference, these interferences are associated with the process of sample nebulization and transport. So during the nebulization process and during the transport of that analyte through that channel of argon passes and everything, there also some physical interference may happen due to your you are just keeping the solution through your micropipettes or microtips or some many finely fine syringe also sometimes you will be using. That contamination also can lead to, that also lead to some contaminations. Okay. So the difference in physical properties of the sample and the calibration solution lead to variation in the aerosol droplet size also. So this may influence the efficiency of the nebulizer and the sample introduction. This efficiency, then sample, how you are introducing into the sample compartment, that also affects a lot. So your chemical interferences, that chemical interferences include the molecular compound formation, ionization effects, and the solute vaporization methods. So chemical interference can be different way, like some other contamination of due to some other elements also can be there. Some way plasma source you are using, some other elements, some or molecular species also getting ionized, that interference are due to chemical interferences. So coming to applications of your ACP-AES, so it is widely used for the agricultural science, where the analysis of agricultural products and foods besides soil analysis also can be done. Till now, in flame photometry, if you remember, mostly flame photometry has been used for the soil analysis part. Soil analysis part. Here, you can also go for the agricultural products and foods besides the soil analysis. And coming to the health science section, determination of aluminum in blood, then copper in brain tissue, selenium in liver, then sodium in breast milk also can be detected. So direct determination of calcium, iron, copper and all these elements can be done in the serum sample. Just now you imagine yourself while studying, we are just seeing like this will measure. But while handling the health science, how carefully you have to do the experimental part, how carefully you have to do, it must be software operated. Mostly software dealing you have to do in a great way. Okay, and sample will be kept in a very like cleaned sample holder you will be using, and various things you have to take care over here in order to study these elements. And geological science also, it is mostly applicable over here. The presence of lanthanides and other elements in rock samples can also be determined. Then forensic science also, it is applicable. Crime scene soil analysis, the way I was telling you, the here crime scene soil analysis means that soil, if something is happening in soil also, some liquid dispersion is there or some blood dispersion is there, from there also many analysis can be done. Like the way I was telling you regarding the use of fluorescence, I was telling you once that in forensic science also, that some burnt body, the extracts of the burnt body where a crime has been done through a brutal murder, as well as your some burning was happened, from the extract of that body sample also you can go for the you can determine the things, the samples, through your fluorescence spectroscopy also. So spectroscopy is having a various applications in many fields, and it will create a job in various lines also, in forensic department, in soil analysis part, many things, in many where you will be finding chemist post for this kind of studies. So in metallurgy area also it is widely used, that is analysis of trace elements in stainless steel. Okay, analysis of trace elements also can be studied in stainless steel. Then environmental science, of course, environmental science you can study wastewater analysis, then determination of pollutant metals in variety of matrices. That is the most important thing nowadays. Water is getting polluted near to the industrial areas. Then you can go for the any kind of water pollutant metal studies by using this ICP-AES. Also, you can use. Apart from that, other fluorescence, other spectroscopic methods also can be used for the water analysis study. Then in industries, these are very useful. That presence of metals like copper, iron, nickels, silicon in lubricating oils and gasoline. See, not only here we need to note down one thing, that we are just seeing these elements can we can study uh, whether it is present or not. Apart from that, in other angle, if we'll think, then if there is any contamination, due to these elements also can be detected. Suppose my lubricating oil A is a pure one and lubricating oil B is the impure one. Impure one means by adding certain impurity, we are making it lubricating more thick and we are selling in the market. Then that contamination you can also catch by doing this spectroscopic analysis. Let me tell you one example. The petrol contamination, okay, or diesel contamination by kerosene has also been studied very well by using fluorescence spectroscopy. There are a lot of research articles, I had seen it. There are a lot of research articles present on this topic, that is your contamination of petrol or by petrol or kerosene, sorry, petrol and diesel by adding kerosene. But the thing is, as I was telling you, the detection limit, you need to note down the detection limit. Okay, by fluorescence spectroscopy, it is sensing 1% contamination of diesel in of kerosene in diesel or petrol. If it is sensing, it's good. If some other method, it is sensing 2%, so other method we may not use. But if some another method, if you are seeing its sensitivity that below 1% of 1% addition of kerosene also it is able to detect, then well and good. So you have to go for that also, not only the detection of these elements, but also you can find out the contamination that is present in your samples or present in other segments like other lubricating oils, gasoline, that also can be studied. So trace of metals like these metals in beer or wine, that can also be studied, because industrial purpose these are very useful to study. And determination of trace elements in polymers, that is evaluation of catalysis and so on, also you can study. So these spectroscopies are having very useful tools. It is a very useful tool to be studied. Now you can see by using this ICP AES, these many elements, you can see these many elements you can study. But you have to see the detection limit. Detection limit for lithium is this much nanogram per centimeter cube, but in other technique you have to go for it. If you want to study magnesium, you have to see what is the detection limit for by going through ICP AES, and what is the detection limit in AS, what is the detection limit in fluorescence spectroscopy, which is better, always go for that. Then other part you can automatically you will be taken care of. So these ICPAEs are having following advantages, that is your rapid and simultaneous multi-element analysis can be done provided the source is suitable for few elements that is coming within that range. Okay, the lack of chemical interferences, mostly when you are using plasma, where the excitation source you see it is very high, the high temperature excitation source, so mostly all atomization is happening. So the chemical interference will it may expected to be minimal over there. Then low sample requirement, very less amount of sample is required for the study. Sorry. Then absence of self absorption and the cause of nonlinear calibration plot in FES, the validity of calibration curves over this order of magnitude, then low detection limit, it's detect up to nanogram per your CMQ or per gram also, then good accuracy and precision you are having, then availability to elements. So various elements you can study, which you cannot study through AS also. Not only this, I want to just tell you that not only this AS or AS, AFS, whatever may be, but the thing is, you need to note down one thing. You have to compare always. You can't say in a general way that, okay, this silver, I'll go for the this SAP AES. You have to go through the literatures. You have to go through the other research papers. Then only you can find out, okay, if my SCP-AES is suitable or not. Because for studying a single element, you have to do lot of things. Sample preparation, then monochromatic things, everything you have to taken care of. Very carefully you have to do, because these things you are going to study for the health science purpose also, environmental science purpose also. So you have to very carefully manage everything. Okay. So coming to the next unit, oh, it is not visible. I have to share it. Okay, just 1 minute. If any question, then you can ask in between sharing. Sorry, this is NMR. This one, application of AS and AS. Okay, this application itself is 1 unit. Very surprising, but it's good that AS and AS is having lot of applications to, we must know. But application is so much, then we have to just see it carefully. But it's good that 1 unit is on that, because you can, if question is coming, then you can answer it in a very good way, right? So easy thing. If you know 2 3 applications, you can elaborate it and narrate it and write it in a good way. Okay, fine. So introduction, will not read out these things because these are the application part as well. So silent features of your AS and AES, this we can see, because question if it is coming, then you need to just see, write in points the silent features of AS. What are these things? It is also a revision kind of thing for you of the last class, whatever we discussed, that is a revision kind here. So AS concerns the absorption of characteristic analyte radiation by the atomized analyte element, and the wavelengths of the calibration observed and the extent of the absorption form the basis of the qualitative and quantitative determination respectively. Of course, the wavelength of radiation that is getting absorbed was the basis of the quantitative and qualitative determination for AAS, that is atomic absorption spectroscopy or spectroscopic method or spectrometry, that measurement of the analyte you are studying. So in flame atomic absorption spectrometry, either an air acetylene or a nitrous oxide acetylene flame is used to evaporate the solvent and dissociate the sample into the component atoms. This also we had seen. And it is not an absolute method of analysis. Last class we discussed about this. This is not an absolute method of analysis. The routine quantitative determinations using AAS are based on the calibration method. Again and again, we saw while studying this AAS also and other atomic absorption spectrometry also. So in addition, the internal standard method and standard addition method are also employed. Last class we saw what is the internal standard method and standard addition method. So compounds of alkali metals, some of the heavy metals such as lead and cadmium and transition elements like manganese and nickel are all atomized with good efficiency by the flame. See, nowadays this heavy metal study is a emerging area. Heavy metal study, like lead, cadmium, all the things. Heavy metal study is a very crucial thing because it doesn't decompose so easily, and its contamination is very very critical for the body also. So, however, a number of refractory elements like vanadium, zirconium, all these things do not perform well with the flame source. So, while studying flame photometry, some elements are not good for through studying through your flame source by using the flame source. However, if you are using graphite furnace source, it may be useful. Okay. So last class how we discussed about the flame source as well as graphite furnace source. So the graphite furnace atomic absorption spectrometry, in which the atomization is achieved electrothermally, is a much more sensitive method as compared to the flame is that we discussed. It is much more sensitive because here we are not using flame, and like in the flames case, your atomization 10% of the sample is getting atomized, but here as soon as you are putting the sample, the light is passing through, so mostly its efficiency is more. Okay, and interference is less, and the higher atom density and the longer residence time in the graphite tube improves the furnace's detection limit by a factor up to your thousand order compared to the flame is. Okay, and the detection limit may extend up to sub ppb range. This is the beauty of the spectroscopic studies. We always go for the detection limit from spectroscopic method to spectroscopy method. If the detection limit is very, 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 very less, then that tool is good to be studied. And GFAS requires a very small sample size. This is also important because that will be cost effective. Because less sample you are using means less cost you are eventually providing it. And it doesn't require any sample preparation. Even solid samples also can be analyzed without dissolution, because you are just putting the sample into the furnace, graphite furnace, then it is automatically then atomization due to electrothermal means happening, then the light is passing through. Then background absorption effects in GFAS are managed by diluting the sample or selecting another resonance wavelength line. So in matrix modifier method, a reagent is added to the sample that may modify the matrix behavior and thereby tackle the problem of your background. Because background noise can be minimized through various ways, and we have to do trial and error how to minimize that. Then accuracy in AS method is generally of the order of zero point 0.5 to 5%, and the precision being 0.3 to 1% at observance larger than zero point 0.1 or zero point 0.2 for the flame atomization, and 1 to 5% with the electrothermal atomization. So it's a robust technique that employs easy to use equipment and can be achieved good detection limit. So these are the silent features of AAS, which we already discussed in the last class elaborately that unit. But here in a comparative and descriptive way, you are going to get a full packet of that AAS. Then coming to the silent features of AES in atomic emission spectroscopy, a reproducible and representative amount of the sample is introduced into the atomization excitation source where it is converted into your atomic vapors of the analyte in the excited state. Okay. And the AES is a versatile method due to availability of wide range of sources. But the thing is, you need to search as the sources again and again. So that is the difficulty part. But the atomization excitation sources are there. So you can change it and detect the various elements. So currently plasma is the most used source, and it is high energy source which is electrically neutral, conducting gaseous mixture, having significant concentration of cations and electrons. And the plasma can be sustained by supplying energy from a suitable external source. Depending on the power sources employed, there are three different type of plasmas. These are inductively coupled plasma, which we saw today, and the direct current plasma and microwave induced plasma. So these plasmas are radio frequency, direct current, and microwave radiation respectively as the power sources. So in order to sustain the supplying energy, you have to use some external sources too. As the energy of the plasma source is quite high, it ensures the excitation of the atoms of all elements present in the analyte. I was discussing just before unit that its source, its energy is very high. So all the elements that are present in the analyte, they all will go for the excitation. Okay, that all will so the atomization, then excitation, then which will emit the electromagnetic radiation characteristic of different elements. So that is why we say it to be multi-element technique. Then argon gas is commonly employed as the plasma gas due to its inertness, simple emission spectrum, then moderately low thermal conductivity and good natural abundance. Two type of spectrometers are used ICP for ICP-AES. These are subsequential spectrophotometer and simultaneous spectrophotometer, where the source of atomization is your ICP, that is inductive coupled plasma. In inductive coupled plasma ICP-AES, the spectral interference due to line-rich spectra of the hot plasma source can be minimized by using high-resolution spectrometers or using alternative analyte lines. These are the minimization things. Spectral things can be minimized. The ICP spectrophotometers are, however, relatively expensive to purchase and difficult to operate. Okay, so this is the limitation with it, but it's a good one to study various elements. Then coming to comparison of AS, the question may come like this. What is AS? You got to know. What is ICP-AES? You got to know. What is its comparison? So here is the table where you can see the comparison of the both the things. That is primarily a single. This AS is primarily a single element technique. Through some instruments with multi-element sources are available. However, mostly single element technique. Here, principally rapid and multi-element technique. This one is. Then here, the flame constituents contribute to the spectral background and chemical interferences. And however, for the ICP AES, then plasma is the optically thin emission source and relatively free from chemical interferences. In the third point, so many points are there. You must remember all these things as far as your exam is concerned. What is silent features of AS? What is silent features of ICPAS? Then what is its comparison? Even if you are remembering this comparison table also, it will be easy for you to remember the silent features. You can write that these things also in the silent features, because eventually it is coming like this. So the dynamic range for the A's, the dynamic range is spread over three order of magnitude for FAAs and two order for GFAAs. And here the dynamic range is large and extends over a range of 4 to 6 orders of magnitude. And for A's, the detection limit are in the range of ppm, whereas it may go down to sub ppb level for GFAS. Okay, and here detection limits are generally very low, that is 1 to 100 nanogram or microgram per liter. Okay. Then flame is easy to set up and use and requires minimal operator skills, and not much skill is needed and easy to set up. And the GFAS is on the other hand is considerably more difficult to operate. That here you will be noting down that the more difficult handling parts means better quality of detection you are getting, and it falls between here AES, it falls between these two AS techniques. However, it is bit easier to master than GFAS. Then this procedure cannot be automated, and this can be automated means through softwares. Then accuracy is not very promising in A's. Here good accuracy and precision we may get. Then here the A's determinations using flames are very rapid and precise and applicable to about 67 elements. However, this AS, it can be used for determination of most elements except argon, and in practice, approximately 70 elements can be determined and not suitable for some elements. However, it is elements that are difficult to study by AS can be measured by AES, because the thermal source you are using is capable of atomizing most of the elements over here. Okay. Mm, okay, contamination during dissolution, and okay, these things I have already told you, that contamination can be of various ways. Then application of AS, then application of AS. Just let me take some water. This unit 11 is completely based on the applications only. So you need to note down how it will be easy for you to remember the things, so that you can pick the things of biological application or your agricultural application, environmental application. One by one, you have to remember in that way. So coming to your AS part, now you can listen to me, so that sometimes if it is just due to hearing impact, something will be in your mind, you can write of your own also. So application for biological samples. So wide range of samples in biological origin are subjected to analytical procedures for the determination of the elements present in the biological samples. Okay, that may include biological sample means not only the human samples, that also may include plant leaves, fruits, vegetables, blood, urine, muscle tissue, hair, etc. So that can be of various type of biological samples. The major difficulty in the analysis of these materials is their complex nature. This is the major difficulty because whatever you are taking, blood or any vegetable or fruit for the study, it is not all, there will be mixture of elements present in there. So how to separate them, how to study them? So it is very, very difficult to study. There must be different procedures for it, and you can eliminate some elements so that it will make you more simpler. Like the way in mathematics we derive some theories. While deriving a certain theory, a certain equation, you will be seeing in between the derivation there are various assumptions. Assuming that this can be neglected, assuming this can be neglected. So you just cut the things and finally you get something. Okay, so that is what you have to do because these things are very complex in nature. So more so, these samples cannot be directly analyzed, but require dry assing followed by wet digestion. So there are various techniques to it. Okay, dry assing followed by wet digestion with the oxidizing acids such as HNO3, HCl4. These are very good strong acids. Okay, first what you have to do, these samples you have to do dry assing. Yesterday I was showing you the heating cycle, the dry assing was there. Then here you can do the wet digestion by using some acids. Okay. In case of blood analysis, plasma or serum, plasma means here blood plasma we are talking about, not that plasma which we used in the spectroscope. So, blood analysis, plasma or serum is generally preferred because of the presence of significant amount of clinically significant elements in them. Because of health science purpose, these are mostly preferred. And here, how to determine the calcium in serum. Calcium percentage goes down if your age is increasing. How to determine the calcium in serum by using this AS. A typical AS determination of calcium in serum is carried out by the calibration method, where a calibration plot is obtained by measuring the absorption of characteristic radiation for a series of standard solutions of calcium in similar matrix. You mean you are going to take some standard solutions of calcium. Okay. By taking the standard solutions of calcium, you are going to get a plot. Then now you are taking the serum. Then after getting the serum intensity, that whatever intensity you are getting in the serum, calcium intensity, then you are just putting that intensity here in the calibration plot. Then by extrapolating it, you can predict the concentration. Then you can know how much concentration of your, you can determine how much amount of your calcium is present over there. Okay, in the serum. So an air acetylene flame is used with a premix burner, and the normal calcium content of serum is generally about 100 ppm. Generally 100 ppm calcium is present in the serum, and it is determined by diluting the sample 1:20 ratio with your SrCl2 solution. See, I was telling you that since because of the complex nature of the biological samples, you have to treat it in various methods. Like for calcium, if you are doing this treatment before the sample is you are introducing in AAS, similarly for other determination, you may have some different sampling technique also. okay, so that you can get a better result. So thus a typical sample would contain about 5 ppm of calcium. Therefore, an equivalent amount of sodium, potassium are added to the standard solutions. The plot is then determine the concentration of the given sample. This is the glimpse of idea or little bit idea you are getting from here. But if you really want to do, then you have to go for the literature studies or article studies where we are doing the calcium analysis in detail. So determination of cadmium is also there. Here you can see like cadmium also there will be some different techniques to it, and cadmium is one of the most important toxic element from the environmental point of view. Calcium is okay. It is helpful in the health science. How much calcium is less quantity calcium is there or not, you are predicting. But which is environmentally toxic nowadays, that are the very important research areas. Okay, so cadmium, it occurs in nature mainly due to volcanic activities. Due to volcanic activities, cadmium is present more, and it is used in plating of metals as stabilizer in polyvinyl chloride pigments and nickel cadmium batteries, alloying. This kind of uses are also there, and it is the prime cause of your itai, the disease that first observed in the Japan. Okay, and the cadmium along with the lead has been most studied element with regard to the human toxicology, as it is no role in plant and human nutrition point of view. If you think you are taking calcium tablets, you are taking calcium supplements, but cadmium supplement, lead supplement, these things we don't need. But as far as human and plant nutrition is concerned, these are not having any role in our body. So you can these are having human toxicology point of view. This is bad for us. So it is highly toxic even if a trace amount is present in the body. That is why we want to study these things more and more. It is most likely to be ingested by your tobacco, smoking, essentially cigarettes. So now you can imagine cadmium, even if it is a trace amount present in body, is not at all good. It's not having any benefit, and mostly it is getting into our body through tobacco smoking and specifically cigarettes. Okay, so I think we all can avoid cigarettes now after this class. Okay, and this absorption of cadmium is higher in females than in males. See, these statements, when we are saying, we are not saying as of our own, or if it is not coming to the text as of its own. Many research are going on. That is, after that only we are giving a statement to it, because there is analysis of the data, and then only you are able to predict something. Okay, so that is the thing. See, quality control boards are there in Japan, USA. Quality control boards are there, which also study these kind of things. Even in Odisha, also in other places, also quality control boards, environmental pollution control boards. Many departments sections are there where the role of chemist is highly essential, who can help them in studying this kind of analytical techniques they can use, and they can go for the detection parts. Okay, so this program, that is why it is having utmost importance. because you are getting idea of all the analytical techniques that can be used for the metal detection, elemental detections. So determination of lead, as I was telling you, that lead and cadmium both are highly toxic element, which is an environmental contaminant, and body also when it enters into the biological systems like plants and animals and reaches the blood, urine, teeth, bones, and animal tissues, etc., it is very, very harmful. Okay, and these materials need to be analytically assessed for the amount of lead so that its damage potential can be ascertained. Okay, it needs to be studied very well, this lead and cadmium, from the viewpoint of occupational and environmental toxicology. The determination of lead in blood is the most important since the concentration of lead in whole blood is considered to be the best indicator of the current lead exposure in human because it is absorbed by the blood so easily. As I was discussing, the woman in women's the cadmium absorption is easy. Here also it is very easy, and it entered to the human blood because of the inhalation of polluted air. Nowadays, lead contamination happened due to polluted air, your food, the fertilizers we are using over there, then water. Through these are less relevant for assessing the health hazards for the humans than the amount of lead actually absorbed. We have to see how much actually it has been absorbed through this kind of things that can be studied through by taking your blood. Okay. See, anticoagulant when we are using heparin, that also a typical lead determination. After adding the heparin, anticoagulant, the blood is treated with the trichloroacetic acid to precipitate the proteins. See, like the way I was telling you in the previous also, so there are some chemical methods before ascertaining or before going for the AA study. Which chemicals we need to add, how you have to do the sample preparation. Zinc in the plant leaves also can be studied by using AAs. Then, as far as biological things are concerned, that was the thing. But environmental samples also can be studied, like analysis of airborne particulate matters, that also can be studied by using AAs. But for everything, like in mercury in air and water, that is a very sensitive issue nowadays, that also can be studied. But before that, you have to do some chemical treatment to that things, then only you can take that solution in the for studying the further atomic absorption spectrometry or through AES. Then whatever trace elements contamination in soil, not only I was telling you, not only you can find out the elements that are present, but also indirect way we can say if there is contamination also we can predict through this kind of techniques. Then biological samples, environmental samples, then industrial samples also can be studied, like determination of molybdenum in steel. Steel is mostly composed of few this carbon and iron, various composition. If some molybdenum is there in steel, that also can be detected. Okay, some examples are given here. Concentration of nickel also can be determined if it is present in that steel. One example with the solution is given that you can see. See, the canned fruit juice. These are not good at all to be used. Even if we know we are using it, we are taking it. Canned fruit juice contain tin in it. Okay, the availability of fruit juice in tint cans is becoming increasingly common, though it is also marketed in cartoons. Many large scale it is getting marketed because it is getting over by us. We are happily drinking that, but it is having tin contamination. As tin is likely to be leached in the acidic medium of juice, the contents of the can get contaminated. Automatically, the fruit juice are acidic in nature. Some people also feel acidity after taking fruit juice. Okay, because that are little acidic as compared to your body fluid. So your tin may get corroded over there in the can, and it may come to the fruit juice also. Hence, its determination is quite important to ascertain the contamination. So that also can be done by using your this thing using AAS. So various application areas there, environmental analysis, that also you can note it down. Then coming to application of AES, similarly the way for AES we had seen for biological samples, here also you can determine the sodium in serum, that also can be determined. Sodium and all we not sometimes determined through As. If it, some elements are there for which we cannot use As, that time we can use this AES very well for determining the solutions. So biological samples we can determine, then geological samples, the way I was telling, some lanthanides and actinides, that also can be sent to your and ICP-AES, and many elements are there which cannot be studied through AAS. You can study here very well, because here the temperature that is implemented through your plasma source is very high, which is good enough for the atomization of many elements which you cannot detect over there. So here are the list of many elements which you can detect through ICP AES, and its detection limits are given. You can see calcium, even if it is present in so small amount means 1 into 10 power minus 7, if I am not wrong, then 1 into 10 power minus 7 মানে this much small amount of calcium if it is present, that also can be detected by ICP AES. Just see about the cadmium contamination, so small amount 2 into 10 power minus 4. Even we can't detect, I don't think we can detect very well through other techniques. Here also if we see lead, which is very poisonous, okay, 0.001, so less amount we can also detect very less quantity of the things in your through this ICP AES. This is a very good technique actually, but the thing is you have to handle it very carefully. Then environmental samples also can be studied by using your this thing, trace amount elements in airborne particulate matters also can be studied, like high concentration of if your barium, strontium, these things are there, arsenic. So various these things you can do, but the thing is, as I was telling you, you have to go through some sample techniques, like you have to collect it, dry it, or to wet it, or some buffer solution you have to add, or some chemical solution you have to add. Then only you can go for this kind of studies. But pre-treatment, we say it to be pre-treatment before moving further things, because why pre-treatment is needed, because biological samples and these samples are complex in nature, it will have various things in it. So if we can do pre-treatment, then we'll get better result. Then industrial samples also you can use, that determination of metals in lubricating oil. I was discussing for AS also. Okay, that also can be done. If lubricating oil is having some contamination of other elements, that also can be detected. Okay. Here in the rock samples 5 element, just list down what you understand by a metal analysis method, give the significance. Oh, we came to summary part. Okay, fine then. So these are the applications and terminal questions. So many questions are there. So many questions with answers. Very good. So terminal questions and answers are already there. Some useful books. Okay, books is fine, but then in every material you are having question and answers. So you can study it very well. So now we can discuss if you are having any questions. So tomorrow we'll discuss the NMR spectroscopy, mass spectroscopy, and then some structural elucidation. We left with the 3 units. Okay, that 3 units will cover tomorrow. With that, I will finish this MCH 003. Then thank you. MCH 003 I will finish. Then MCH 002 maybe other sir, Prakash sir will be taking that class. Then tomorrow is our last class. We'll try to finish these 3 units in tomorrow. I'm running in hurry also because 3 more units are there to complete. So any question? If not, then I will just stop the recording.
No, ma'am.
Okay, fine, fine then. Thank you, all of you.
Thank you, ma'am.
Tomorrow we'll just study this NMR first, then mass spectrometry, then
Okay,
we'll
ma'am.
move to the structural elucidation. Okay.
Okay, ma'am.
Mhm.
Okay, ma'am.
Thank you, ma'am.
Thank you, thank you.